Welcome to the approximately, I would say, 75 of you who made it to this class out of 500 or so. I hope that you didn't do some horrible commute to get here. I hope that it was fairly straightforward. But yeah, congratulations on having made it, because it's not nice outside. OK, so today we're just going to do some more symbolization stuff. So we're just going to clean up some loose ends from the symbolization stuff that we've done before, and also a little bit more, and then just a bunch of examples. We'll just run out the clock doing as many examples as we got time for. So that's the plan today. I do have your tests once more. If you want to pick them up at the end, you can sort through. Best of luck to you. Your fellow students did not leave them in alphabetical order for you, so it'll be a bit of a hunt. But hopefully you can find yours. You're also welcome to come to my office hours to pick them up. That's also a place where you can go to get them. They won't have them at Logic Lab because I'm not there to let them into my office to give them the tests. But my office hours are a good place to get them. OK? Course business, any questions before we start? OK, let's dive in. So let's talk about this thing that, so there's a little bit of discussion of this on the discussion board on Quarkus. Let's talk about combining universals. So we're specifically talking about, as we said, universal affirmative statements. And this is one of the, I believe this is one of the exercise questions. Certainly somebody wanted help with this to understand why Logic 2010 demands that you do it the way that it does. And the answer ultimately is going to be because of the limits of Logic 2010, not because of the limits of logic. So I'm going to show you at least two ways of symbolizing this that I'm going to try to demonstrate are logically equivalent to each other, exactly as good, but unfortunately Logic 2010 only accepts one of them. But here we are. OK, so here's the sentence. Doctors and lawyers who are rich are admired only if they're also honest. OK. So, and there the symbolization scheme is there. So, recall from last time, so there's a little bit of a review. This is a relative clause. The who are rich is a relative clause, right? And is it restricted or non-restrictive? Sorry, restrictive or non-restrictive? It is not. So are we talking about, is the topic of this sentence, so the question to ask yourself is, if you're looking to symbolize this sentence, is this sentence talking about only those doctors and lawyers who are rich? Or is it saying about doctors and lawyers that they are rich and also something else? So it's the second thing. The second thing. So this is, we're not restricting our focus only to those doctors and lawyers who are rich. We're saying the topic is doctors and lawyers. That's the whole topic. And we're saying two things about them. One, that they're rich, and two, that they are admired only if they're honest. Yeah? So that's a non-restrictive relative clause. OK. Now, so here is one perfectly good way of symbolizing this. So this captures the non-restrictive relative clause. Has got two things that it's saying. You might want to symbolize that as two separate universals. The one on the left says, if anything is a doctor or a lawyer, note the or, despite the fact that it says doctors and lawyers. We talked about this last time because we want the scope to include things that are both doctors and things that are lawyers. So if anything is a doctor or a lawyer, then it has this property that only if they are, they're admired only if they're honest, which is to say, if they are admired, then they're honest. Yeah, so that's the left-hand side of that conjunct. And then we're saying this whole totally separate thing that also about doctors and lawyers, that they have the property of being rich. OK, so that is a perfectly good way of symbolizing this sentence. And if you type it into Logic 2010, it will tell you that it has no idea what you're talking about and that you've got it completely wrong. So sorry about that. If there was a way to tell Logic 2010 that more answers are good, I would have done so, but there isn't. So nonetheless, if you do this on the test, you see a non-restrictive relative clause. It's saying two things. So you combine them in a conjunction. That's a perfectly reasonable way of saying two separate claims, put them together with a conjunction. OK. So what does Logic 2010 want you to do here? Here's what it wants you to do. So the second line there is logically equivalent to the first line. So it says, if anything is a doctor or a lawyer, then that thing has these two properties, the conditional and the property H. Yeah? So in the first line, we've got this conjunction that says, if anything's got F or G, then it's got this conditional property. And if anything's got F or G, then it's got this property H. And on the second line, we've just put them together. We've said, if anything's got the property F or G, then it's got both of these properties. One is a conditional, and one is just the property H. OK. So I want to clarify why these things are equivalent. I mean, hopefully it's reasonably intuitive, but I'm going to translate, if it's OK, I'm going to translate this back into sentential logic to show you the equivalence. So when you're asking if two universal statements are the same, they've got all the same variable, it's all just x here, so just one variable is in play, you can just ask, are the things inside the brackets logically equivalent? And if everything inside the brackets is logically equivalent, then those two things are logically equivalent. So suppose we do this. Suppose we say fx or gx is a sentence P. And if jx and kx is the sentence Q. OK? So we're just simplifying what's being represented here. So that top line just says if P then R and if P then Q. It says if this antecedent is true, then this thing. And if this antecedent is true, then this other thing. Is that equivalence fairly clear? And then the second one just says if P, then Q and R. OK, so now the question is, are those two sentential logic sentences equivalent? Are they logically equivalent? And yes, they are. So here's a theorem, theorem 29. There's a biconditional equivalence between if P, then Q and R, and if P, then Q, and if P, then R. So this is one of our theorems from back in sentential logic. Right, so those two things is a fact of logic that those two things are exactly equivalent to each other. That is, if the atomics have the same truth values, then one side has the same truth value as the other. Yeah? Is this helping at all? OK. 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 This is just, I'm really just trying to give you a stripped down version of these somewhat more complicated universals to make the logical equivalence between these two ways of representing the sentence as obvious as I can. So just to go back, so this top sentence says, if this antecedent, my microphone has just died. OK. Now I have to stand at the podium because these were the only batteries that were left. My apologies. One sec. Unless anybody has two AA batteries on them. No one? People don't bring batteries to class anymore? God, kids these days. All right. OK. OK, so I'm going to do the rest of this lecture from the podium so you can hear me. OK, so the first sentence, the first big complicated thing, just because there's two universals doesn't make it logically different than if you combine them under one universal, under the scope of one universal. Yeah? So two logically equivalent ways of symbolizing the non-restrictive relative clause in this sentence. Yeah? OK. So just to drive this home, so if two universal affirmative statements have the same topic, the same antecedent, then they can be combined into one big universal affirmative with a conjunction in the consequent. So whatever the if they've got identical antecedents, then you can just combine the consequence using a conjunction. Is that okay? Again, the tragedy of Logic 2010, it's so useful, it's so helpful, but I saw, so this is based on, this question was asked on the Quarkus discussion board. Somebody else asked a similar question where Logic 2010 wanted the combined universal for this question. Somebody asked another question where it wanted two separate universals, which is an annoying fact. So it doesn't have a uniform preference for doing it one way or the other, but it does insist that you do it one way or the other. On the test, on the exam, logically equivalent answers will all be accepted. Yeah? So we are smart and sensitive enough to see that you've done a sensible thing and give you full credit for it. Okay? Okay. I hope that helped at least a little. Okay. Right. So that was just to try to clear up some stuff from last time. Here's some new material. Number. So this is something that we could have done back in predicate logic, actually, or sorry, sentential logic. And I'm going to do this largely in terms of sentential logic. So this will be a blast from the past, good old-fashioned sentential logic. It'll nonetheless be useful for doing predicate logic. In predicate logic, we've got really good tools for symbolizing all and more than none. We've got the quantifiers to do that. So if you want to symbolize the fact that all of something have a property, we've got the quantifier, the universal quantifier, and of course, more than none of something, we've got the existential. But what about more specific numbers? We've got some work to do to understand how to symbolize, for example, at least one of P, Q, and R. So how do you symbolize, if I want to say at least one of Jane, Bill, and Ted went to the party, how do you symbolize that? Okay, so at least one of. At least one is compatible with more than one, right? If you say at least one of these people, at least one of you passed the test. That's true. It's weird to say it that way because many of you passed the test, but it's logically compatible, right? So at least one just says more than 0. Okay, so how do we symbolize that? Well, fairly straightforwardly, right? We can just say, but try to get the general principle here. So if I say P or Q or R, under what conditions is that sentence true? Under the condition that at least one of P or Q or R is true, right? If any one of them is true, then the whole sentence comes out as true. So if I'm going to symbolize at least one of P, Q, or R, you just put them together with disjunctions. Yeah? So in general, we're going to do this with all of these numerical properties that we're trying to represent. What we do is just sort of like try to figure out what all the possible cases are and come up with a logical representation that gets all of the relevant cases. Right? So we're enumerating cases and trying to represent all of the relevant ones. Okay. How about at least? At least 2 of P, Q, and R. At least 2. So, slightly trickier. At least 2 is, of course, and just to note, at least 2 is compatible with 3 of them, right? At least 2 of P, Q, and R is compatible with all 3 of them, yeah? Right? At least 2. I'm going to need at least 2 of you to blah, blah, blah. That means if 3 of you did, that's fine. Or if 2 of you did, that's fine, but not 1 or 0. So we want to come up with a representation of this that is true just in case 2 or 3 of P, Q, and R are true, but false if 1 or 0. Okay. So how about this? Okay, slightly more complicated, but hopefully still reasonably intuitive. So that whole sentence is a collection of disjunctions. The whole sentence is true if any one of those cases is true. And what we've done here is just pick out, there's only 3 possible situations in which at least 2 of these things are true. And here they are. Here's all 3 of them. Okay. So here's a worry that you're probably having right now. What if all 3 of them are true? So what happens to that sentence? What happens to the truth value of that sentence if all 3 of P, Q, and R are true? It's true, right? So if only P and Q are true, then the first disjunct, P and Q, is true, which makes the rest of the sentence true, because with the disjunction, you just need one part of it to be true. So if just P and Q are true, the whole sentence is true. If P, Q, and R are all true, then P and Q is true, P and R is true, and Q and R is true. So the whole thing comes out as true. If only one of P, Q, or R is true, then none of those conjunctions gets to be true, right? None of those conjunctions is true because you need both of them to be true for that conjunct to be true. Therefore, all 3 fail, and the disjunctions come out as false as well. So if just one of them, or if none of them are true, then the whole thing is false. Is that good? Okay. Okay, so that was at least 1, at least 2. I mean, if you have, we're not doing anything more than 3. It's logically possible to do like at least 17, but let's not do that because that is very cumbersome and annoying. So I'm not going to give you any of these that you need to deal with more than 3 things, okay? I hope that you can, if you're interested, you can imagine how to extend this general framework to more than 3 things, but I'm only ever going to give you 3 things to deal with, okay? Okay, so at most one of P, Q, and R. Okay, so what does at most say? It says, what are the cases that are compatible? So here's how you deal with these questions from kind of first principles. You ask yourself, what are the cases that are compatible with at most 1? It's saying there's not more than 1. So 0 is compatible with it. None of these being true is compatible. And 1 of these is being true is compatible. So we want to rule in 0 and 1 and rule out 2 and 3. Yeah? Okay. Now, that's kind of annoying to represent, to be honest. You're going to have to like enumerate a whole bunch of cases. So it's helpful to notice the following. So notice the following. 1 or none of P, Q, and R is true is equivalent to at least 2 of them are false. Right? So we can use the representation that we just had for at least to capture at most by just putting negations on them. We just flip it. So it looks like this. So here's the long, annoying way of doing it. Basically, you just enumerate all of the possible cases. Say P and Q are false and R is true, P is true and Q and R is false, P and R are false and Q is true, or P and Q are false and R is false as well. So we want to also capture the case where there are 0 of them are true. So that's the long way of doing that. But given that we just noticed that at most 2 is equivalent to just the flip side of at least 2 are false, right? We can do this. Okay, so at most 2 of P, Q, and R is equivalent to at least 1 of them is false. So instead of doing that 4-part conjunct, let's do at most 2. So at most 2 is equivalent to at least 1 of them is false, right? And not P or not Q or not R is equivalent to not P and Q and R. So it's just the negation of the whole thing. So P and Q and R says all three are true. If we're going to say at most two, you're just ruling out the case where all three are true. Yeah? And don't do the thing on the bottom line. It was helpfully pointed out to me that the thing on the bottom line doesn't work. Thank you. So the thing on the bottom line doesn't work. Why? Somebody who didn't already point this out to me. What case does it fail to include the possibility of? If I want to say at most two of P, Q, and R are true, the thing on the bottom line doesn't work because it says either P is true and Q and R are false, or P and R are false and Q is true. What if none of them are true? If I say at most two of them are true, that's compatible with all of them being false. So the thing on the bottom line doesn't work because it doesn't include the possibility of all of them being false. Yeah? So don't do that. The first two lines do work, though. Yeah?
And it's possible that only one of them is true.
Yep. Yep. It's possible that only one of them is true as well. Yeah. So we just need to rule out the case where all three of them are true. To get at most two, we just need to rule out the possibility where all three of them are true. Yeah. Okay? Okay, so, and one last thing, exactly. Exactly one of P, Q, and R. I don't have a clever way of shortening this. I don't have it's long, and what I got there is kind of long and cumbersome, but I don't know of any way of making it less long than that. You just enumerate all of the possible cases. There's only three possible cases where exactly one of P, Q, and R is true, and here they are. Yeah? Where one of them is true, just all three cases where one of them is true and the other two are false. Yeah? Again, it's a lot to memorize. If you're just going to, I mean, it's perfectly legitimate to just memorize these. That's not a terrible way of going about this. But I think it's probably easier for you and more worth your while to just think about the general principle that we've been talking about with all of these. So what you do is ask yourself, what are all of the possible cases? What are all the possible cases that are compatible with the thing that I'm trying to represent and incompatible with them? And just kind of, you can just, I mean, this is what we've done here. We've just said, okay, I'm just going to go through all of the possibilities and say it's this one or this one or this one. Huh? Thrilling stuff, I know. Okay. And exactly two, it just works exactly the same way. You just enumerate the cases where two of them are true and one of them is false. Yeah? So I do think that this is a slightly different way of using logic than we have before, in the sense that you're having to think by, like, you're not directly representing the sentence say exactly two of this, this, and this. What you're doing is coming up with something that is true in case the thing which you're saying is true, and false if the thing that you're saying is false. Right? We're in some sense just representing all the possibilities of the sentence that we produce, rather than doing a more straightforward representation of the content of the sentence. Right? So we're kind of building a logical little scenario, sets of scenarios that are compatible with the thing we're trying to represent, rather than the more straightforward just saying what the structure of the sentence is. So so what I'm trying to point out is that if I say exactly two of P, Q, and R, there's no or in that sentence, is there? And there's no and in that sentence. So what you're used to doing when you're doing symbolizations is picking out these indicator words, and, or, but, if, only, right? And just saying, here's the operator that I'm dealing with. But we're using symbolization differently here. There's no and in that sentence. There's no, what, exactly two of PQ and R. Well, there is an and, but that and doesn't work the way it normally works, right? We're having to kind of brute force imagine the scenarios that are logically compatible with what we're saying and represent those scenarios rather than representing the structure, the explicit surface structure of the sentence you're presented with. Yeah? So just like with that, just like with the thing that we started with this thing about when are two sentences logically equivalent, right? It's just that whenever one is true, the other is true. Right? You could do a biconditional between the two. That means that they're logically equivalent. And in general, that's what we're trying to do with our symbolizations. So this is just trying to expand what we do with symbolizations a little bit. If you've got a really clear sentence that you can just pick out the ands and ors and buts, then you can just take the surface structure of the sentence as your guide to symbolization. What we're doing here is a little more advanced. We're trying to find something logically equivalent to the meaning of the sentence. Okay. It's perfect. If that's all weird and not to your liking, you can just memorize this stuff. But I hope that the general principle is fairly clear. And it's a general principle about what we're trying to accomplish with our symbolizations. We're trying to accomplish coming up with a sentence that's true if the sentence is true and false if the sentence is false, rather than explicitly representing the structure of the sentence as it's presented to you. Okay? I think that's all the stuff about quantity. Oh no, there's a little bit more. Okay. Okay, so just really quickly, let's go over the difference between not all and none of, because those are very different claims about how many of a thing there are. So not all, so it's a negated universal, is not the case that for all things in the universe, if fx, then gx. It's not the case that all f's are g's. And that's made true by there being more than 0 things in the universe that are f's and not g's. It just needs to be 1, and that whole sentence comes out as true. So not all students are sleepy. If there's at least one alert student, then that sentence is true. It's very, very different than saying none of the students are sleepy. I see one of you who's literally asleep right now. So I know that that's false. I'll try to talk quietly. Okay. So none of says, if I go through the whole universe, there's literally nothing that satisfies it, right? So none of the F's are G's. None of the students are sleepy. That's true only in case there are 0 students who are sleepy. So just get this. I mean, I hope this one's intuitive. I hope this one's fairly straightforward. The difference between not all and none of. Yeah? Is that good? Okay. Okay. And just one last, very, very similar. Some blank is not, and it's not the case that something is. Some blank is not versus it's not the case that something is. So there exists at least one thing that is an F and is also not a G. There exists at least one student who isn't sleepy. Right? That's true if there's one student who's not sleepy. Compare that to, there does not exist a thing that is both F and G. There's no student who's sleepy. Clearly false. Yeah? So this is just the, really this is just the exact same thing as the last slide, but quantifier negated. So we're just using the quantifiers in opposite ways here. Good with this? Questions about any of this stuff? Okay, good. So the rest of the class, we're just going to do a bunch of symbolization examples. All right. Okay, so let's just, by way of review, at least 2 of James, Tara, and Sam went to class. This is nice to review that stuff about at least that we just did. It's also nice to review the fact that so we're doing this in predicate logic now, that not all of our predicate logic sentences are going to be quantified. This is predicate logic, but it doesn't use quantifiers because we're talking about specific names for things. And we haven't reminded ourselves of that for a little while, so probably good to like get this back fresh in our mind. I mentioned it at the beginning of predicate logic, and then everything that we've done since has been quantified, has been general sentences. But this is a particular sentence. We're talking about specific things, specific people, in fact. So at least 2 of James, Tara, and Sam went to class. Okay, so this is going to be something about people going to class. That seems clear. So if we want to say that James went to class, that would be, oh, stop. That would be CJ. If I want to say Tara went to class, that's CT. And if I want to say Sam went to class, that's CS, right? Okay, now we just have to recall how we talked about at least 2. At least 2. Okay, so at least 2 is compatible with which cases and incompatible with which cases? That's the question. Anytime that you, suppose you're on the test, you're looking at one of these questions and you totally forget how to do this stuff. Here's how you do it again from first principles. So imagine yourself sweating, nervous, regretting your life choices. All right. So what are the cases that are compatible with at least 2? So compatible and incompatible. All right, at least 2, well that's 2, right? That's certainly compatible. And then 3 is also compatible, right? So we got to capture both of those cases. We want to rule out what? 0 and 1. Okay, so we need a representation that gets these and rules these out. All right, how do we do this? So we can literally just brute force it. So again, I'm imagining that I've utterly forgotten everything in this that I taught you before about the general forms of this. I'm just going to try to brute force it. So I'm going to say, well, CJ and CT and CS. That's one of our cases. Okay, so we got all 3. Now we have to say, to somehow rule out, so you can say that or 2 of them. So CJ and CT or CT and CS or CJ and CS. That's this thing. How's that? Yeah?
Do you need that first part?
Good. No, you don't. No, you don't. So once we've got these 3 things, we've got this and this and this, if any one of those are true, then, like, okay, so suppose this is true. So, sorry, I approached that the wrong way around. Suppose this is true. Then at least one of these are going to be true, right? Actually, all 3 of them are going to be true, right? So by capturing the situation where we have at least 2, or like one or the other of them, we've also captured the case where all 3 of them. So you could just leave this out. So there. Okay. Now we ask ourselves, so that captures the case where at least two of, like, CJ and CS, so James and Sam, James and Tara, Tara and Sam. Okay, those are all the possible scenarios where two of them went to class, and that also gives us where all three of them. Does this rule out the possible cases that we wanted to rule out as well? That's the second test you have to ask yourself. So yeah, okay, we've got the cases that are compatible. Did we also capture the cases that are incompatible? Well, if 0 of them went to class, then this is false, and this is false, and this is false. So good, yeah. That makes the whole sentence false. That's what we wanted. We wanted to be false when the original sentence is false, right? So if nobody goes to class, it's false that at least 2 of them went to class, right? And if only 1 of them went to class, all 3 of those conjuncts still come out as false. Yeah? Because you need at least 2 of them to have gone to class in order for one of these conjuncts to come out as true. So there we go. Yeah? Interesting, yeah, okay, so good. So here's another way we could have done this. CJ and CS and not CT. Or CJ and CT and not CS. Or, sorry, there should be not CJ and CS and CT. Oh, my handwriting is just getting terrible. Okay, but that would have been, right, logically equivalent to what we have there, right? Or at least it captures the same cases. So it rules out any case where 0 or 1 of them showed up, and it rules in, but we need one more, don't we? We need one more to make this work, because we haven't captured the case where all 3 of them go to class. So we need one more conjunct, CJ and CT and CS. Now we've got it. Yeah? Okay. And again, you do have the option of just memorizing what's on the slides, or you could do this somewhat more labor intensive, but nonetheless reasonable working out of all the possible cases. And I promise, again, I'm not going to give you anything where you have to deal with more than 3 things. So there's not all that many. There's only 4 possible cases in any of them. So, okay? Okay. Let's do another. Let's not do another one of these. Oh, no. Okay. That's enough of that. Okay. Dogs and dolphins jump only if petted. All right. So, questions to ask yourself right off the bat. Is this so there's no names here. So your clue that you're dealing with a non-quantified sentence is if there's a bunch of names in there. That's potentially not a general sentence. But this one doesn't have any names. It's just predicates. So we know that there's at least a quantifier. And now you ask yourself, which quantifier is it? Are we talking about a couple of dogs or a couple of dolphins, or are we talking about the class of them? It's the class of them, right? It's the set of all dogs and dolphins. So we know it's a universal for all x, something, something. Now, and now that we know that we've got a universal affirmative, we know that it's going to be a conditional, right? Because that's how you symbolize a universal affirmative, with a conditional. Unless it's one of those really weird ones that's just everything in the universe has this property. If it was everything in the universe jumps only if petted, then that would be just a conjunction. But in here, we've narrowed it down to less than the entire universe, right? We're talking just about the dogs and dolphins. So, of course, we're going to say IX. We're not going to say IX and DX, right? Or IX and KX. Because that's talking about, so if we said IX and KX, then something, something, then we would be talking about everything that is both a dog and a dolphin. I think that would be a very cute animal, but it does not exist. That's not what the sentence is talking about. We want to say IX or KX. Okay, so if something is a dog or a dolphin, then something something. Jump only if petted. Okay. So the consequent is itself going to be a conditional. It's got an only if in it. And we're just going to remember our good old-fashioned sentential logic symbolization skills and recall that whatever comes after only if is the consequent, which makes this the antecedent. So if something is a dog or it's a dolphin, then if it jumps, then it was petted. All right? So the topic of the sentence is dogs or dolphins, anything that satisfies the predicate dog or satisfies the predicate dolphin. We're saying of that entire class of things, that broadened class, that it has the following property. That in any case where it jumps, it must have been petted. How's that? Questions? Yeah.
How do you know that dogs and dolphins is the first antecedent?
Right. Because it's the thing that, so the question is, how did I know that this was the antecedent? How did I know that dogs or dolphins is the antecedent? It's because I'm trying to figure out what the topic of the sentence is. So I'm relying on your ability to discern, so all sentences have a kind of subject-object structure. There's a subject of the sentence, and then there's a thing you're saying about the subject. And I'm just relying on your ability to identify which part of the sentence is doing that work. That's something that you've all got the implicit skill of, if not the explicit ability. If you've done linguistics, then you've got that explicit rules for that. But typically, just as a speaker of a natural language, your ability to say, here's the topic of this sentence, and here's what's being said about that topic. So I just read the sentence, dogs and dolphins jump only if petted, and thought, that's about dogs and dolphins. That's what that sentence is about. I'm sorry, I can't be much more explicit than that. I didn't do linguistics, so I can't get any more technical than I looked at it and figured it out. Yeah. Okay? Okay, let's do another. Oof, gross. Yeah, let's do this one. Let's do this one. Okay. I'm going to do this one again because it's got this fun thing in 2 commas. We're getting good at this now, right? If something is between 2 commas like this, we're saying Billy, so the topic of the sentence is Billy. We're saying, who isn't picky, ate some greasy chicken for lunch. Okay, and that, because it's between those 2 commas, it is a non-restrictive relative clause, right? So we're making 2 claims about Billy here. Lucky him. It's clearer in this case than the ones you're used to because it's obvious that we're not talking about the topic of Billies who aren't picky, right? That should be obvious. We're not talking about the class of all Billies who aren't picky. We're talking about one specific dude, Billy. We're saying of him that he's not picky and that he ate some greasy chicken for lunch. Okay, so let's do this. For all x, no, do we need that? Actually, we don't need that. Let's not start with that. Let's first do the fact that Billy isn't picky. You don't want to quantify that sentence. You want to say it's not the case that B has the property B, right? We're saying of a specific object, Billy, that he does not have the property being picky. Yeah? Okay? And then we're saying and 8 some greasy chicken, 8 some, should be some. Ate some greasy chicken for lunch. Okay. Now, we are certainly not saying that Billy ate the set of all greasy chicken for lunch. Fortunately for Billy, he would die. We're saying there exists at least something such that it is greasy chicken and Billy ate it, right? So there's an existential for us. There exists an X such that it's got the property of being chicken and it's got the property of being greasy and it's got the property of having been eaten by Billy for lunch. There we go. So we'll have a more elegant way of symbolizing things like this when we get to two-place predicate logic. So if I had this as a two-place predicate, I say A was eaten by B, then I could say D, then X was eaten by Billy. That's how we would symbolize that. We'll get to that after the next test. In this case, we just built it in that the property, it's a weird property, D, being eaten by Billy for lunch. But that's as best as we can do right now. Okay? Quick questions before we're done? Yeah?
Okay, let's say Billy's a category, so you're saying Billies who aren't picky.
We'd have to have different predicates for that.
I'm not sure, like, why specifically are we using picky as its own, like, why are you symbolizing it that way?
So there's not a principle. So we could make the categories of all things that are Billies into a predicate. There's no logical reason why we can't do that. It's just that given this symbolization scheme, so you're always doing symbolizations relative to a symbolization scheme. If I don't give you a symbolization scheme, if you get to make up your own, do you know how you symbolize every sentence? P. That's it. If you get to decide your own symbolization scheme, here's how you can symbolize literally any sentence. P. It's very easy. But given this, so it's always given a symbolization scheme that we're doing these symbolizations. Does that answer your question? So there's no principled reason why we didn't have a different symbolization scheme. That's just the one I assigned. Yeah?
No, I was asking why you're using isn't picky as the non-restrictive. Why not restrictive?
Oh. Well, the reason why it's a not restrictive, it's a non-restrictive relative clause is because it's between those two commas. That was our convention, that if something is between two commas, it's as kind of a side. Yeah? So we also don't have in this symbolization scheme the class of all Billies, which is what you would need in order to represent it as a restrictive relative clause. We'd have to say all of the Billies that are picky. And I didn't give you that option here. So that's why it's fairly clear that you can't do that. Does that answer your question? Okay, good, good. Okay, we're out of time. I do have your tests, so if you want to come pick them up, you're welcome to.